Whoops. Okay. Let me put this on Discord for us. And let me go get bond enthalpy. This will be for this class. Okay, so what did we think about the exam? I have not looked at the average yet. I can do that later, but what did we think overall about that? Good, horrible? Pretty easy? Awesome. It's good to hear. Yeah, I told you guys exam 3 would be easier for sure. It's first of all only 2 chapters, and then it's mostly trends or stuff you could look up pretty easily, so that's good. Okay, awesome. So let's go ahead and get started today. So it's been almost a week, right? We had kind of talked about molecular shapes and bond angle and all that sort of fun stuff. Let's just do a couple of them. Let's see if we can do let's work on these 2 molecules and let's figure out the Lewis structure, the electron geometry, and the molecular geometry for these 2 molecules. So let's go ahead . Okay, we've got 5 things around this phosphorus, right? So we're going to want to bond these so that we do not have any outer atoms that have unpaired electrons. So doing this, we get technically this structure. So we do not have any lone pairs on phosphorus. So this would fall under the category of AX5. And so let's see if we can't try and remember maybe what this shape is going to be. If we forgot, in Discord, somewhere in here, is our handy chart. So, and in fact this particular molecule is written there, but AX5, or 5 electron domains with no lone pairs, is right here. So we would find it and see that this should be trigonal bipyramidal. So up here, remember, is the number of lone pairs on the top. That's your E value. And they've written coordination number as the y-axis here, or like y side. That's the same thing as like x plus E. So the number of electron domains you have. So looking at that, we can say, okay, this is going to be trigonal bipyramidal. Both electron plus molecular, they're going to be the same because there's no lone pairs, right? So if we were to draw it with happy, nice shape, we would draw it as the trigonal pyramidal shape would be, which has one up, one down, one to the side, and then kind of one going towards us, one going into the board. or tablet or whatever. So this would be like the most correct Lewis structure showing the shape, and we would get our geometries would have our electron geometry and our molecular geometry from this. So I know this is completely forgotten by now, but oh well, we'll keep working. All right, so if we take sulfur with 4 fluorines, I guess I need lone pairs, huh? Oh, by the way, if we were to calculate the formal charge on all these, there would be 0 formal charges, so we're okay. There's no craziness, no double bonds or anything needed for this. We have a phosphorus that has more than 8 electrons, but nothing we can do about that. Alrighty. So if we go ahead and do this, just because I'm weird, I just want to do that so that we don't have to break another lone pair and then have to pair them up later. I think it'll just be easier to leave the lone pair alone. Throwing that together. This is what we end up with. If we ever finish drawing our lone pairs. So looking at this, this would be AX4E, right? We have 4 outer atoms, 1 lone pair. So we know electronically this is trigonal bipyramidal. Just like before, 5 domains, coordination number of 5. Same thing as before, coordination number 5. Electronically, it's trigonal bipyramidal. And if we look at the chart, how many lone pairs do we have? We have 1 lone pair. So we're going to go down this chart now, or this column rather, and we're going to see, oh, okay, so we have a trigonal bipyramidal that has 1 lone pair, which will be the structure that I'm kind of circling here, which is technically called bisphenoidal, but people often just say seesaw instead. And so let's go and look at our seesaw. So that's telling us that typically we draw the seesaw as having the lone pair directly up. Actually, that should be, if that one's going straight up, yeah, then these can be in the plane, and these would just be going down. Thousands of lone pairs. What do we think the bond angle is going to be on the top of that molecule there? Oh, I see what's happening. Technically, one of these is going to be in and out, just like before. Okay. What do we think the bond angle is going to be over here? So between that fluorine, the sulfur, and the fluorine. Just go ahead and take a guess. So previously our PCl5, if we were looking at the angle between these 2 chlorines and the phosphorus, should be 180, right? Now we have a lone pair in the way though. And so if you remember, lone pairs are actually going to push stuff a little bit down, right? So this is actually going to just be a little bit more than 180. I don't know the exact number. You would not be expected either, but that should be a little bit bigger than 180. Because remember, lone pairs push stuff away more than atoms do. So technically, we would probably want to draw this, if we were really crazy, not selenium, we might draw it something like this, where it's just a little bit pointed down. Just to illustrate that that lone pair is pushing stuff a little bit away. So the bond angles are not going to be the same as they were for the regular trigonal bipyramidal. For this one, it's going to be a little bit bigger than 180 as a result of that lone pair pushing down. So I'll write that again. Remember, lone pairs, they push more than atoms do. And so it's going to kind of push those fluorines a little bit down. Here, let's actually look this up. Let's see. SF4. Let's see what we get here if we look at this. I don't need you guys to see Chem 101's homework. I think this is, yeah. Okay. Let's see what our angle is going to be. So it's 173 on the other side, which means it's going to be 186.9. Technically on that side. If this angle down here is 173, the angle on the opposite side would be a little bit bigger than 180, right? So there we go. That is going to be our bond angle there, or yeah, our angle there. Do we have any other fun stuff? No. Yeah, so you can see here again in this kind of structure, we have the fluorines a little bit tilted away because of that lone pair being pushing down on it. Okay. I ain't lying. So in this case, it happens to be 186.9, but just bigger than 180 is what I was going for. Okay, so as a result, this would be like a better way of drawing it. So for these, it's kind of just practice. You need a lot of practice on these just to get them going. So, while it would be nice to, do an example for every single one on this chart, we simply will just not have the time to do that. So I will kind of have to leave you to, in your homework, to go through all of these. So for this particular chart, we are given example molecules for all of these. And so we have in the leftmost column, that's going to be your electron geometry for all of these. And as we start adding in lone pairs, or rather substituting lone pairs in for atoms, we're going to have these other shapes in the other columns. And so we're going to see there's examples for all of them. So you may want to, just as practice, go in and take SO2, take NO2 minus, take ClF5, and try and draw these things so that you can get these shapes that are on the left of those molecules. And same thing with, the ICl4 minus and all that fun stuff. So if you can draw all of these molecules and get the right shape, you'll be good. So, you may want to make a little worksheet for yourself, give yourself all of these molecules to draw, and here is your answer sheet right here. So you can just go ahead and clarify that you're getting things correct or not. So that would be my recommendation for doing this, just to practice with kind of learning these shapes. Of course, you'll have access to this on your exam, so you're not going to necessarily have to memorize all the different shapes and geometries and all that, but still would be a good idea to be familiar with them. I hear one outside, but it's probably Gumbo coming in to steal food, so I'm not going to let him in. Okay, so I'm going to just write here angrily. Practice. There we go. That is my angry yell for the day. So, definitely a good thing here. Practice as much as you can. That'll help this kind of really solidify in your mind. With the answers, with the answers there, you should be able to hopefully figure out what you're getting wrong. And again, I'm happy to address ones that are problematic. Alrighty. Do you guys want to visit thermochemistry again? I think it'd be pretty cool. Let's do that. Actually, I guess I should draw. We'll draw it as the snail. Back to thermochemistry we go. It's just one little bit. So with all these bonds, covalent bonds, let me enthalpies have been calculated. Let's see if Wikipedia has a nice bond enthalpy. Bond enthalpy. Do we have a nice table? Oh, what are all these? Oh, these are. Let's see if there's like a data table. Bond enthalpy data table. No. I will find you a good one. How about bond energy? Was that what we're going for? No. Okay. I was really hoping Wikipedia would have one, but here's a random website. Let's show it to you guys. I'll find you a good website if I like, whatever. Oh, these are this is really concise. Oh, I see. So we're going to see that all of these bonds are going to have enthalpies associated with them. So that would be the energy that's required to break those bonds apart. So breaking bonds always takes energy. And so all of these quantities are always going to be positive. So we can see there's just a bunch of, random, values here for these bonds. So I'll show you how to use them in a little bit. I'll find a good table. I'll put it on. Your book has a nice table, but since it is in the book, if some of you don't have that, I will find you a new one to work with. So the fun part about this is we can calculate delta H reaction using bond enthalpy. And so that's going to be the sum of bonds broken. Or let me just do it this way. I'm sorry, did I write that the wrong way? Yes. Oh no, now I'm... So it's going to be the bonds we're forming minus the bonds we're breaking. So forming the bond is just going to be the negative equivalent. So what this means is that all of this, these values here, they're positive. Those are how much it takes to break the bond. So to form the bond, it's just the opposite. So if you take two H atoms and put them together to form an HH bond, you are going to release 435 kilojoules of energy per mole of atoms. So just just understanding that your enthalpies here are going to be different depending on which kind of one you're looking at. Now that I think about it, I think I have this switched around. No, it should always be broken first. Broken, yeah. Yes. Okay, and in that case, we're just going to leave everything as it is. This negative thing will already be taken care of. So I'm going to just erase this because I don't want you guys to get confused. So let's go ahead and try and figure out what the delta H for this reaction is going to be. Let us take methane and make we'll make chloromethane and hydrochloric or hydrogen chloride. Forming bonds is always exothermic. So we're going to see basically based on which bonds we're forming, which bonds we're breaking, what is happening here. So we can see from this first one, it's actually best to draw the Lewis structures for this type of thing so you can see exactly what's happening. So from this, let's look at our things. Let's see what we're breaking and what we're forming here. So let's do broken in purple. Oops. No. Go away, Google Assistant. No. Okay. So which bonds are we breaking here? Looking at this. So anything that we're breaking is not going to be present in the final bit here. Yeah, exactly. So we're going to be breaking this bond here, and we're going to be breaking this bond here. So we're breaking our chlorine apart, and we're breaking one of the CH bonds in methane. Bonds that we're forming is going to be this one and that one. Right? The rest of the stuff is staying the same. So this tells us that we are breaking a CH bond and a Cl-Cl bond. We are forming a CCl bond and an HCl bond. So if we go ahead and swap over to our table, again, I'll choose a table and put it up for you guys, but for right now we'll just use this one. Let's find CH on this. Looks like it's right here, so that'll be 414. I'm just going to copy these numbers over. Oh god, Gumbo is outside trying to break in again. Chlorine is right here, 243. CCl is another one we're dealing with. That's 331. And HCl, where are you, HCl? Here we are, 431. Okay, so I've just copied the numbers over. These are all kilojoules per mole. So just looking at these numbers, we're probably going to say this is going to be an exothermic reaction, right? We are breaking bonds that are roughly 650 kilojoules, and we're making about 760 kilojoules as a result. So if you remember that we're going to do is going to be our broken minus our formed. That's going to be 414 plus 243 minus 331 plus 431. And while Kevin, oh my god, he's already got it. Okay. Is it really that much? Are you sure it's not 171? Wait, I don't see how that makes sense at all. Did I copy the numbers wrong? Because just looking at it, the ones place we get a 7 there and a 2 there, so it should end at 5. Double check that, Kevin. I'll do it too. And we'll have Tyler and Shane also do it. Just so we're there. Minus 331, minus 431. I got negative 105. Did I write the numbers wrong? Oh god, I got the same as the snail. Does that mean I'm wrong? Okay, Kevin got it this time. Okay, cool. Yeah, so that would be for this overall reaction, wherever it happens to be, this one forming the chloromethane, that would be our delta H for that reaction. Hateful indeed. But this is not too bad, right? It's just using these Lewis structures to see what bonds we're forming and what bonds we're making. Let's do the same thing with bromine. Let's see what happens. Okay. So this is why we're doing the Lewis structures first. So enthalpy is, or thermochemistry, unfortunately, will always come back to haunt us. So bonds we're breaking. I'll do in purple again. Breaking kind of the same bonds here. And we're going to be making two bonds, which are here. So we're breaking a C and H bond and a Br-Br bond. We are making a CBr bond and an HBr bond. So we do have the value for CH, which is 414. And the others we're going to look up. Alrighty, so, well, just for now, I'm going to go ahead and put that website in Discord for you. I may or may not choose to use this one. I don't know how, if this is extensive enough. That's what I'm trying to say. So I'm going to put this in extra resources. So any of you who are following along right now, if you want to use the same table I'm using, it is in extra resources on Discord. Discord, I think, is window 2. Yeah, it's right here. So if you want to look at that table, it's in our extra resources area right down there. Okay. So let's go ahead and look at that table. So Br-Br bond, let's see if that's on here somewhere. There it is, 193. CBr bond is here at 234. And HBr is over here at 364. Okay, so here are the numbers we've gotten. So just like before, that's going to be the ones broken minus the ones formed. Let's see who's going to win this time. Let's go ahead and do the math. 414 plus 193 minus 234 minus 364. Oh, 9. Yes, exactly. So this one is actually endothermic. And this one here is exothermic. Where are we? Just for fun, as we should always be afraid of when I say that, let's compare what would we get. Oh, yeah, this is a problem, Tyler. Let's do this with delta HF too. Let's just see if we're on the same idea. So let's look at these delta HFs and see if we are going to have the same answer here. And I'm really hoping we do. I haven't done this in advance, but let's see. Do you remember how to do delta H reaction using HF? We're going to have products minus reactants, right? So let's go ahead and bust open Discord and see if we can't find the thermodynamic quantities. So let's see, we're looking for, so bromine we already have is going to be standard. HBr is one we're going to need. So for HBr, I'm just write the reaction. Let's see, delta HF for HBr is negative 36.2. We had all these carbon ones. We had methane here is negative 74.8. Negative 74.8. What else do we have in this reaction? Br2 is already going to be in its normal state. And then we have, oh gosh, CH3Br. I'm not sure if that will be here. Let's Google it. CH3Br HF. Oh. Wow, are we going to have to do this from the beginning? Okay, you know what? This is going to take too long. So forget it. I tried. I wanted us to actually. Yes, we already know delta H reaction, right? We could solve for it if we really wanted, right? So delta H reaction would be HF for bromomethane plus HF for HBr, our products, minus this, right? If we know that delta H reaction was 9 kilojoules, we could solve for HF. See how I saved my problem when things went awry? Where's HBr? Negative 36.2. Minus negative 74.8. And so HF for delta HF. Remember, we don't do bromine because it's already in its natural state. It just has HF of 0, so who cares? What's it look like, Kevin? This should be a delta in front of all these, of course. Awesome. Oh dear. How did we get... Well, it should not be less than 1. We don't typically see such small ones. So make sure you're just adding and subtracting. Yeah, okay, cool. So it looks like that's the number we get. So there we go. Woo, I saved my ass by translating it to a different problem. So we're good. Alrighty. You thought you were done with thermochemistry. That's really funny. So, okay. Do you want to do one more bond enthalpy one, or are we good to move on with our lives? While Gumbo shrieks out there. He knows there's food in here, that's why. Because these other dogs decided to only eat half their breakfast, so. What do we want? Another problem with the bond enthalpy? Or something else? Either way, okay, let's just do one more then. Let's make it a complicated one. Let's use our bond enthalpies here. Much more complicated problem. Alrighty, so we can also do this for more complicated systems. Let me just find the balancing. I don't want to balance it myself. Combustion of propane balanced. Okay, it's 5 oxygens and 3 carbon dioxides, 4 waters. Okay, cool. So, if we look at this, we are going to break 1, 2, 3, 4, 5, 6, 7, 8 CH bonds. We are also breaking 2 CC bonds. Do we all see that? For this molecule, we're breaking those 10 bonds. So we're breaking 8 CH bonds, and we're breaking 2 carbon-carbon bonds. I guess it's a good idea that I did a more complicated one, right? So that way we're not going to be totally lost on our homework. So since we only had 1 propane, that's technically how we would do it. I'm going to just do this for oxygen because that's how many oxygens we have there. So we are technically breaking 5 O double bond O bonds. I'm going to just draw a line here so we get not too confused. Fine, I'll do it for all of them. If we look at this, we are forming 1, 2, 3, 4, 5, 6 C double O bonds. And we are forming, sorry, let me draw all the waters out just to make it super clear. We're going to have 8 OH bonds. So this stuff here is broken, and this stuff here is formed. So is that okay? Can we, like, if you also, by the way, if you're looking at your water, and you know each water molecule has 2 OH bonds, you could just multiply that by the coefficient here, and you would get 8 OH bonds that you're forming. You don't have to draw them all out every time. So same thing like before, we know each oxygen molecule, we're going to break 1 O double bond O bond. I feel like I said bond 5 times in that sentence. And we're going to have 5 of them, so it would be 5 overall. Okay. So let's go ahead and understand that our delta H reaction here is going to be broken minus formed, right? Bond, James bond, exactly. So we're going to have 8 CHs plus 2 CCs plus 5 oxygens minus 6 C double bond O's plus 8. Actually, I'm just going to make it, I'm going to not have to worry about all these crazy parentheses. Minus 8, what are they, OH bonds. So now with all this Lewis structure information, we can use these to figure stuff out. Okay, so back to our chart. Let's look up what these values are. Where did the chart go? I think it was here. Okay, we have CH, which we probably all have memorized now, is going to be 414. CC, single bond, 368. Oxygen double bond, 498. C double bond O, 532. And OH. Oh no. Aha! Thank goodness it's right here. 465. Can you hear him like squealing behind the door, by the way? Shrieky Gumbo. So this would be 8 times 414 minus, plus, sorry, 2 times 368 plus 5 times 498 minus 6 times 532 minus 8 times 465. So while Kevin is doing that, and he's already got our answer for us, heat of combustion of propane. Let's see, heat of combustion. Where are you hiding? Enthalpy of... this table doesn't even have... That's... Ooh, I got it. Apparently this is quite a much bigger number, Kevin. Really, is it 374? This doesn't seem right. Did we balance it correctly? Well, whatever. Apparently we get 374, so we'll just leave it at that. It seems lower than it should be. I hope... Oh... No, I think... Well, I'll look into it. If anything's weird, I'll let you know. But there we go. We have done it. Hooray! Cool. Did we have any questions on that one? So we can use these Lewis structures to kind of illustrate basically how we can use thermochemistry again to solve for our delta H's. Hooray. Okay, no questions? Alrighty, then we're going to now talk about bonding some more. Alrighty, so we're going to talk about how stuff forms covalent bonds. And so let's look at chlorine. We know that chlorine has... what noble gas? Neon, I think. 3s and 3p, right? So both of these chlorines have this electron configuration, right? So we're going to see that the electrons that are going to bond in chlorine are 3p electrons. And so we're going to see that in order for covalent bonds, can you hear the squeaking? He's driving me nuts. Maybe you can hear him scratching at the door. Okay, good. Let me see if I can have him removed. Okay, let's see if we can have someone get him out of here. In the meantime, to form covalent bonds, orbitals must overlap. So, if we're looking at p orbitals, remember that p orbitals are kind of, what shape shall we use? Yeah, we'll use purple. P orbitals are kind of this dumbbell shape, right? And so in order for chlorine to kind of bond, these bits will have to overlap. We need an overlap to happen. So these are going to be 3p orbitals of chlorine that need to come together for it to bond. So what's going to happen is they're just going to get nice and close, and lo and behold, there is our bond. All right, and so hooray, that is what's going to be called a sigma bond. I don't know why I wrote that in purple also. Here, I'll switch that around. This is a sigma bond. Something we kind of refer to as a single bond. Single bonds are always going to be sigma bonds, but for right now, let's just accept that. And so that's going to be this nice overlap between them. So for chlorine to form that single bond, it's got these 3p orbitals that each have one electron in them, and they're going to come together and pair off and make that nice bond within them. And so we're going to see that p orbitals bond with p orbitals, and s orbitals bond with s orbitals. But let's take a look at something. We know this guy exists, right? Methane. If we look at hydrogen, it's just 1s, right? It's got its one electron. For carbon, we have, I'm just going to do the valence because who cares about the rest of it? We know CH4 exists, and there are 4 single bonds in the CH4 molecule, right? It's a nice tetrahedral, happy, plain old methane. If we can only bond s orbitals with s orbitals and p orbitals with p orbitals, how the heck are we going to get the s orbitals to bond with these guys? It's kind of a tricky situation. What will actually happen is, in order to bond, so we know that carbon is going to make those 4 bonds, right? So we're actually going to, those 2 s electrons can bond with the hydrogens already. That's no problem. It's these p electrons that are tricky. And so yes, that is one thing we could do, Kevin. We could promote hydrogen electrons into a higher energy state, but that is a bigger energy gap than what we are about to do. And what will happen is that these orbitals are actually going to form hybrids. So we know that 2s is lower energy than 2p, right? What's going to happen when they hybridize is we're going to end up making a new orbital that has all 4 orbitals put together of kind of a medium energy. So while the 2s electrons were lower energy than the 2p electrons, we're actually going to make what are called Sp3 Hybrid Orbitals for this particular molecule. So we're going to mix, basically, mix an s orbital with 3 p orbitals. And that's how we're going to get this kind of sp3 thing. And so we're going to see that, in fact, we're going to have 4 electrons in there. And we're going to use these 4 electrons because these are hybrid orbitals. They can actually bond with the s orbitals because there is a portion of all these orbitals that is s. right? So approximately like 25% of an sp3 orbital is s, right? Just by how much they are. And so that is where this overlap is going to occur. So we're going to see that actually s or sp3 orbitals, which are hybrid, look like this. We have this kind of like sad little bit here that we're not going to really deal with, and we're going to have this nice happy blobby shape. So that's what happens. We've basically just, oh gosh, we've basically, oh my god, I can't draw figure eights. Okay, there we go. I'll draw them as real eights. So s orbitals are spherical, right? So that's going to end up, for whatever reason, looking like this, where we have kind of a dumbbell that's distorted now. And so this shape, the sp3 hybrid, will be able to bond. So this is PPP. They're just 3p orbitals. Here's an s orbital. We now have sp3 orbitals, and we're in fact going to have 4 of them. That looks like a p orbital. Let's fix that. Looks like I'm just drawing ugly fish or something. So we're going to end up forming these hybrids. And so we're going to see here that these sp3 can bond with either s or p orbitals. And so if we were to think about it, we would not be able to react carbon with hydrogen if its electron configuration was what it was on the left. This tells us we would make, we would probably make 2 bonds with those 2 s electrons, and we'd have 2 p electrons that are just kind of hanging around, maybe as a lone pair or something. And we know that, in fact, we end up making 4 CH bonds of equivalent energy. And so this idea that we're hybridizing the orbitals to make 4 equivalent energy ones helps us, or it explains why methane will make 4 CH bonds that are all equivalent to each other. And so we're really going to see that this is going to be the case for almost everything that's bonded together. We're going to see that for any kind of like, let's just say this, for most heteronuclear, that means different atoms, different elements rather, molecules, hybrid, hybrid orbitals are used to make single bonds. And in fact, I'm not sure that I want to say this, but even for most homonuclear ones as well. You know what? So let's just erase this condition, because a lot of homonuclear ones will also use hybrid orbitals. So, and that's to make single bonds only. We're going to see for double bonds or triple bonds, we used unhybridized orbitals. And so, technically, God, do I want to start talking about other hybridizations right now? Kind of, I do. But I don't know if I'll have enough time. No, let's just leave it here today. So tomorrow we'll continue on with this unhybridized good stuff by talking about what double bonds look like. Oh, I know what I could finish on. One thing that I kind of neglected to maybe explicitly point out for you guys. If we go back to that table of bond enthalpy, notice, well, just look at these 3 right here. So a carbon-carbon single bond versus double bond versus triple bond, we see that the more bonds we have, the stronger the enthalpy is, right? It will take a lot more energy to break a triple bond than it will to break a single bond. Right? It's roughly 3 times as much, a little bit less, but we see there's an almost like additive relationship here. If we have a second bond, it's almost the same as 2 CC bonds. And if we have a third one, it's almost the same as 3 CC bonds. There's a little bit of difference there, but the more, the higher your bond order is, that is to say, a triple bond will have a more energy, or it takes more energy to break a triple bond than a double bond, and more for a double bond than a single bond. And that's the case for all these. So we can look at same thing with nitrogen, triple bond 950, single bond 297, double bond oxygen 498, single bond 213. So it's always more energy to break multiple bonds within a molecule. And we're going to see that. I know I don't want to talk about that. And it turns out also that in terms of bond length, a triple bond is shorter than a double bond, which is shorter than a single bond. So we're going to see that tomorrow when we start talking about these unhybridized orbitals. This is going to be an exciting thing. We're going to talk about molecular orbital theory, which is also a pretty hairy topic, but it's not that bad. Trust me, we'll get through it together. Nothing is as bad as thermochemistry was with the calorimetry problems. So this stuff may seem complicated. I understand. I've just introduced it. We're going to talk about it more tomorrow. I'll show you very easy shortcuts to get around thinking about these hybrid things. So, yeah. Cool. Cool. So I'll have I given you homework for Lewis structures yet? I don't think so. So I'll put some up for you guys so you can cry about that. Practice your shapes and all that fun stuff. So we'll have that going for you. And we'll pick up this stuff tomorrow. Talk more about hybrid orbitals and then molecular bonding theory. Hooray. Alrighty. Cool. I will see you all tomorrow.